Standing at the base of the Great Pyramid of Giza, staring up at those colossal limestone blocks, each weighing as much as a dozen cars, it's impossible not to feel a sense of awe. How did ancient builders, without cranes or computers, achieve such perfection? The joints between the stones are so tight you can't slip a credit card between them, and they've held firm for over 4,000 years. This isn't just a relic of the past. It's a silent challenge to everything we think we know about human capability, and the pyramids are just the beginning. Across the globe, from the Andes to the deserts of Egypt, ancient civilizations left behind structures so advanced, so precise, that even our most cutting-edge technology struggles to explain them, let alone recreate them. Think about the last time you saw a modern construction site towering cranes, hydraulic lifts, laser-guided tools. Now picture a team of workers carving a 900-ton obelisk from solid granite using nothing but copper chisels and sheer muscle. Or imagine shaping a stone wall so precisely that not even a razor blade can fit between the joints, all without mortar or adhesive. These aren't myths or exaggerations, they're real feats of engineering that defy logic. The truth is, we've lost something profound: knowledge so sophisticated that it vanished with the civilizations that mastered it. What if I told you that some of these ancient techniques remain unsolved puzzles, frustrating even the brightest engineers of our time? That's exactly what we're about to explore. This isn't just a history lesson, it's a detective story, a journey into the minds of the ancient world's greatest builders. We'll uncover 24 construction secrets that modern machines still can't replicate, from the earthquake-proof walls of Machu Picchu to the mysterious acoustics of hidden chambers deep within Egyptian temples. Each one tells a story of ingenuity, persistence, and a level of craftsmanship that borders on the supernatural. So if you've ever wondered how the impossible was made real, or why we still can't match the brilliance of our ancestors, you're in the right place. Hit play and let's unravel these ancient mysteries together. High in the Andes Mountains, the walls of Machu Picchu stand as a silent testament to the Inca's genius. Stones weighing tons, carved and fitted together so perfectly that they seem to merge into a single, unbreakable surface. What makes this even more astonishing is that they achieved this without mortar, without metal tools, and without the precision instruments we rely on today. Instead, they used an almost intuitive understanding of geometry and physics. Each stone was painstakingly shaped to interlock with its neighbors, creating a puzzle where every piece absorbs and redistributes force. When earthquakes strike, and they do frequently in this region, these walls don't crumble. They actually dance, shifting slightly before settling back into place, as if the stones themselves are alive. Modern engineers have tried to replicate this technique with computer-aided designs and laser measurements, but something always falls short. Machines can carve stones with near-perfect edges, but they lack the subtle variations. The Inca builders intentionally included tiny bumps, slight curves, and asymmetrical angles that actually strengthen the overall structure. It's as if the Inca understood something we're only beginning to grasp. Perfection isn't about rigid uniformity, but about harmony, and their walls don't just defy earthquakes, they've outlasted entire empires. Take the famous 12-angled stone in Cusco, another Inca masterpiece. It's not just a show of skill, it's a functional marvel. The intricate cuts allow the stone to distribute weight evenly, locking the wall together in a way that resists shifting and cracking. No modern construction method, with all our steel reinforcements and shock absorbers, has managed to match this level of resilience using nothing but raw stone. Even more baffling, the Inca had no written language, no blueprints as we know them. Their knowledge was passed down through hands and eyes, a living tradition of craftsmanship that vanished with their civilization. So the next time you walk past a brick wall or a concrete building, think about this. We may have skyscrapers and hydraulic cranes, but somewhere in the Andes, there are walls built by hand that have stood unshaken for centuries. And we still can't figure out exactly how they did it. Now picture this giant stone faces, some taller than a 3-story building and heavier than a space shuttle, silently watching over an island in the middle of the Pacific. Easter Island's Moai aren't just sculptures, they're monuments to an engineering puzzle that still stumps researchers today. How did the Rapa Nui people, with no wheels, no draft animals, and no metal tools, move these 80-ton colossuses miles across uneven volcanic terrain? The most baffling part isn't just the weight, it's the journey. Some of these statues were hauled uphill from quarries to ceremonial platforms, navigating steep slopes and jagged rock. Modern engineers have tried to recreate the feat using every theory imaginable. One popular idea suggests the statues were walked upright, rocked side to side with ropes while teams pulled them forward. Experiments show it's possible but painfully slow. Another theory proposes log rollers, yet the island's sparse tree cover makes it unlikely they had enough timber to lay a continuous path. And then there's the mystery of the broken moai, dozens abandoned along ancient roads, as if whatever method they used sometimes failed catastrophically. What's even more fascinating, the Rapa Nui didn't just move these statues, they perfected it. Oral histories describe teams chanting in rhythm, coordinating pulls with near-military precision. Recent studies even suggest the island's roads weren't flat but slightly concave, acting like natural tracks to guide the moai's base. Yet when modern teams try these methods, the logistics collapse. Without the Rapa Nui's intimate knowledge of balance, friction, and teamwork, the statues tip, ropes snap, and progress grinds to a halt. Think about that for a moment. We live in an age of cranes and hydraulics, yet we still can't match the efficiency of people who worked with nothing but fiber ropes and sheer determination. It's a humbling reminder that ancient builders didn't just rely on brute force, they mastered physics in ways we're still deciphering. And somewhere on Easter Island, hundreds of moai stand as silent witnesses to secrets we've yet to fully uncover. Beneath the Mediterranean waves, 2,000 years after the fall of Rome, something extraordinary defies the laws of time. Ancient harbor walls, still intact, resisting the relentless erosion of saltwater. While modern concrete crumbles in decades, Roman piers and breakwaters endure, their strength only deepening with age. The secret, a recipe lost to history, then rediscovered by accident. Roman engineers mixed volcanic ash from the Pozzuoli region with lime and seawater, creating a chemical reaction modern scientists call the miracle of crystallization. Tiny mineral fibers grow within the concrete over centuries, filling cracks before they can spread. It's not just durable, it's self-healing. Today's engineers face a paradox. Our concrete, reinforced with steel, corrodes faster in seawater than the Romans' bare mixture. Laboratories have spent decades reverse engineering samples, only to hit the same wall. The missing ingredient isn't just volcanic ash, it's the specific way Roman builders combined materials. They didn't just toss components together, they understood ratios, curing times, even the mineral content of local volcanic deposits. One breakthrough came when researchers noticed traces of aluminum in ancient samples, suggesting the Romans used a rare type of ash with unique binding properties. Yet even with this clue, modern recreations lack the same resilience. Consider the Pantheon's dome, the largest unreinforced concrete structure in existence. After 1900 years of rain, earthquakes, and pollution, its interior remains flawless, no cracks, no sagging. Modern architects can't replicate this feat without steel supports, yet the Romans built it with a lightweight aggregate, even varying the concrete's density from base to apex to distribute stress. But here's the real twist: their concrete wasn't just stronger, it was greener. The chemical process absorbed carbon dioxide over time, making it more eco-friendly than our carbon-intensive modern mixes. So why haven't we adopted this ancient wonder? Partly because Roman concrete set slowly, taking years to reach full strength, a timeline incompatible with today's fast-paced construction. But also because we're still piecing together their knowledge, fragment by fragment. In a world obsessed with progress, it's humbling to realize that an empire without calculators or chemistry labs might have mastered a technology we're still struggling to decode. Every time a modern seawall cracks or a bridge fails prematurely, it's a silent reminder that the past holds secrets we've yet to reclaim. The Great Pyramid of Giza doesn't just impress with its size, it baffles with its precision. Imagine a structure so perfectly aligned to true north that its sides deviate by less than a fraction of a degree. To put that in perspective, even modern architects using GPS and laser-guided tools would struggle to achieve such accuracy. Yet the ancient Egyptians managed it over 4,000 years ago without compasses, satellites, or even the concept of magnetic north as we understand it. How? That's a mystery that's kept researchers awake for centuries. One theory suggests they used the stars, tracking the movement of certain constellations to pinpoint celestial north. The pole star we use today, Polaris, wasn't in the same position back then due to Earth's wobble on its axis. Instead, Egyptians might have relied on a pair of stars circling the north celestial pole, using their positions to triangulate true north with painstaking observations. Another idea points to shadows, a simple yet brilliant method involving rods and the sun's path. By marking the shadow's shortest point at midday over several days, they could draw an exact east-west line, then bisect it to find north. But here's the catch: even with these theories, replicating the pyramid's precision is nearly impossible. Modern experiments show that star-based methods come close but still leave tiny errors, and shadow techniques are vulnerable to atmospheric distortion. The Egyptians either had an undiscovered method or a level of patience and skill we can't fathom. Some researchers speculate they used water-filled trenches as natural levels, aligning the pyramid's base with the horizon's reflection. Others argue they might have had access to advanced tools lost to time, like finely calibrated sighting instruments. What's undeniable is the result, a monument that has stood for millennia as a silent testament to their genius. While we debate the how, the pyramid's alignment remains a humbling reminder that ancient knowledge often outstrips our assumptions. We might have technology, but they had something equally powerful: an intimate, unshakable understanding of the world around them. The hanging gardens of Babylon, legendary terraces bursting with lush greenery, cascading waterfalls, and exotic trees rise like a mirage from the desert sands. Ancient texts describe an oasis so magnificent it left travelers breathless, a feat of engineering that turned one of the driest regions on Earth into a thriving botanical paradise. But here's the twist: despite being celebrated as one of the seven wonders, no physical trace of the gardens has ever been found. Not a single brick, not a scrap of irrigation piping. This absence fuels one of history's greatest debates. Did they ever exist at all? And if they did, how did Babylon's engineers pull off the impossible? The central mystery isn't just the garden's beauty, it's their water. Babylon received less than 10 inches of rain annually, yet accounts describe vines draping over towering stone terraces, their roots perpetually quenched by an invisible network of channels. Greek historians like Strabo claimed a revolutionary screw mechanism lifted water from the Euphrates River to the highest tiers, powered entirely by human labor. But modern experiments reveal a glaring problem. Even with teams working around the clock, lifting enough water to sustain such a vast garden would require a system more advanced than anything else from that era. Some theorists propose hidden aqueducts or underground cisterns, while others argue the gardens might have been a poetic exaggeration, a royal propaganda piece to awe visitors. Yet the intrigue deepens when you consider the alternative theories. One radical idea suggests the gardens weren't in Babylon at all, but in Nineveh, built by the Assyrian king Sennacherib a century earlier. Cuneiform tablets from his reign describe an elaborate system of bronze screws and canals that redirected mountain springs into terraced gardens eerily similar to later Babylonian accounts. Archaeologists have even found remnants of such structures in Nineveh, complete with stone aqueducts etched with garden imagery. If true, it would mean the Hanging Gardens' legacy was borrowed, repurposed by time and storytelling. But let's assume for a moment that the gardens did exist in Babylon. The real marvel isn't just the water supply, it's the delivery. To keep plants alive in that climate, the system would have needed perfect precision. Too little water and the gardens wither, too much and the heavy terraces risk collapse. Modern hydraulic engineers have tried to model it using period-accurate tools, but the math never adds up. Without pumps or waterproof cement, preventing leaks or maintaining consistent pressure seems unworkable. Unless, of course, the Babylonians had a technique we've yet to rediscover, something as simple as layered clay pipes, or as ingenious as capillary action harnessed through porous stone. What's haunting is that even if we someday uncover the truth, the deeper lesson remains. Ancient builders routinely achieved what we dismiss as fantasy. Whether the Hanging Gardens were real or myth, their legend persists because they represent a boundary, one where human ingenuity clashes with the limits of nature. Today, with all our desalination plants and drip irrigation, we've reshaped deserts into farmland. But in the shadow of Babylon's vanished wonder, there's a humbling question. Did we invent these solutions or merely reinvent what was lost? Standing on the windswept plains of Salisbury, Stonehenge's towering blue stones seem to defy logic. These massive slabs, some weighing as much as a small truck, didn't originate here. They were hauled over 150 miles from the Preseli Hills in Wales. That's like dragging a loaded semi-trailer across mountains, rivers, and thick forests without wheels, without roads, and without modern machinery. And that's just the first half of the puzzle. Once they arrived, these stones were somehow lifted into perfect alignment, positioned to capture the solstice sun with eerie precision. How did Neolithic builders accomplish this 5,000 years ago? The answer remains one of archaeology's most tantalizing riddles. One popular theory suggests sledges and rollers, teams of workers dragging stones atop log tracks, lubricated with animal fat to reduce friction. Experiments show this method works sort of. Small teams can move multi-ton stones short distances, but the sheer scale of Stonehenge's journey introduces brutal complications. The route from Wales to Salisbury crosses unforgiving terrain, including steep slopes and waterlogged valleys where logs would sink or snap. Even with hundreds of people pulling, maintaining momentum over such a distance seems implausible. Then there's the glacial theory. Perhaps ancient ice sheets carried the bluestones south, depositing them nearby. But geological surveys reveal no evidence of glacial activity in the precise area where Stonehenge stands, leaving this idea on shaky ground. The mystery deepens when you consider the stone's final arrangement. Each upright megalith had to be raised into position, then capped with equally massive lintels, a process requiring perfect balance and coordination. Modern engineers have tried replicating this with Neolithic tools, only to watch ropes fray, timbers crack, and stones tumble. The builders likely used a frame levers and counterweights, but the exact technique remains speculative. Even more baffling, the lintels aren't just plopped on top, they're connected with intricate tongue and groove joints, a woodworking technique applied to stone with flawless precision. But the real genius of Stonehenge isn't just the how, it's the why. The monument's alignment with the summer and winter solstices suggests it functioned as a celestial calendar, tracking seasons with astonishing accuracy. On the longest day of the year, sunlight pierces the heel stone to strike the altar at the center, a feat requiring mathematical knowledge we didn't think Neolithic cultures possessed. Some researchers argue the alignment couldn't have been accidental. It implies generations of astronomical observation passed down orally without written records. Today, with cranes and GPS, we could build a replica of Stonehenge in weeks. Yet without blueprints or metal tools, Neolithic people achieved something far more profound, a timeless marriage of brute strength and celestial wisdom. Their methods may be lost, but their legacy endures a silent challenge etched in stone, daring us to unravel its secrets. Deep beneath the rocky landscape of Cappadocia lies an ancient marvel that redefines what we think of as urban planning, not towering skyscrapers, but a sprawling underground empire carved by hand into soft volcanic stone. These hidden cities, some descending over 18 stories deep, weren't just crude shelters, they were meticulously engineered metropolises, complete with ventilation shafts that breathed fresh air into the lowest chambers, wells tapping into underground rivers, and secret tunnels allowing entire populations to vanish from invaders. What's staggering isn't just the scale, it's the foresight. Without blueprints or surveying tools, builders orchestrated a subterranean world where thousands lived for months at a time, all while modern machinery struggles to replicate even a fraction of their precision. Take Derinkuyu, the most famous of these cities. Its labyrinthine corridors connect homes, stables, churches, and even wineries, all stacked vertically like layers of an inverted pyramid. The ventilation system alone is a masterpiece, shafts dug at exact angles to create natural airflow, preventing stagnation while masking smoke from cooking fires. Modern engineers have calculated that duplicating this passive ventilation would require computational fluid dynamics software, yet the builders achieved it through trial and observation. Even more impressive, the massive stone doors wheel like slabs that could roll shut to seal off passages in times of danger. These weren't just barriers, they were counterweighted to be moved by a single person, yet strong enough to withstand sieges. The real mystery lies in the coordination. How did teams working in pitch darkness with nothing but bronze tools and oil lamps maintain consistent ceiling heights, avoid collapsing adjacent chambers, and align tunnels across multiple levels? Recent laser scans reveal something astonishing. The cities follow a fractal-like pattern, with major arteries branching into smaller passages in a way that maximizes space and minimizes structural risk. It's a design principle modern subway systems use, except Cappadocia's builders applied it over 2,000 years ago without mathematical models or GPS. What's humbling is that today, with diamond-tipped drills and 3D mapping, we still can't excavate with this level of harmony. Modern underground projects often require reinforcements like steel beams or concrete linings, yet these hand-carved tunnels have stood for millennia without a single column for support. The rock itself was their blueprint, its natural faults and densities intuitively understood by artisans whose names are lost to time. Walking through these silent corridors, you're left with a haunting question. Did they possess a forgotten science of stone, or was their genius simply the patience to listen to the earth itself? In the heart of Maharashtra, India, the Kailasa temple at Ellora doesn't just rise from the earth, it erupts from it, a mountain-turned monument by human hands. Carved from a single, massive basalt cliff over 1,200 years ago, this isn't construction, it's subtraction. Workers chiseled downward, removing an estimated 200,000 tons of rock to reveal a temple so intricate, it looks like it was sculpted by giants with toothpicks. Every column, every deity, every delicate floral motif was painstakingly freed from the stone, all without the luxury of error. One wrong strike and the entire vision could collapse. Modern engineers armed with computer-guided CNC machines have attempted similar feats, but even their precision can't match the organic fluidity of Kailasa's carvings, where stone seems to breathe and flow like fabric. What makes this achievement even more astonishing is the temple's scale. The main structure towers over 100 feet tall, with courtyards, bridges, and a multi-story sanctum, all carved from the living rock. The precision isn't just artistic, it's structural. Pillars were left standing at exact intervals to support the weight above, while delicate reliefs were etched with such depth that they cast shifting shadows as the sun moves. Contemporary stone-cutting machines can replicate the sharp angles, but they falter at the subtleties the way a goddess's fingernail curves or the ripple of a stone elephant's trunk, details that suggest an almost supernatural understanding of the material. Theories about their methods range from the plausible to the fantastical. Some scholars suggest they used a grid system, mapping designs onto the rock face before carving, while others point to ancient texts describing specialized chisels hardened by secret alloys. But the real mystery lies in the speed. Based on tool marks and historical records, researchers estimate the temple took just 18 years to complete. That means workers removed an average of 50 tons of rock every day, a pace that would challenge modern jackhammers, let alone Iron Age tools, perhaps the most humbling detail. The builders left no blueprints, no trial pieces, no evidence of mistakes. Every strike of the chisel was confident, as if they could see the finished temple hidden within the stone. Today, with lasers and 3D modeling, we can analyze their work down to the millimeter, but we still can't answer the fundamental question: how did they make the impossible look effortless? Standing in Kailasa's shadow, you're left with the eerie sense that some secrets aren't just lost, they're waiting to be rediscovered. Stretching across the arid plains of southern Peru, the Nazca lines are a gallery of giants, colossal figures of spiders, monkeys, and geometric shapes so vast they can only be fully appreciated from the sky. Some stretch over 1,200 feet, their lines razor straight even when crossing hills and valleys. The mystery isn't just their size, it's how the Nazca people, 2,000 years ago, crafted these geoglyphs with near mathematical precision without ever seeing their work from above. No drones, no hot air balloons, no way to check their progress from the air. Yet somehow, they translated small-scale designs into desert-spanning masterpieces that defy erosion and time. Modern attempts to replicate the lines reveal just how difficult this feat truly is. Teams using GPS and aerial photography still struggle to maintain proportions across such distances. Even slight errors in angle or curvature become glaring when scaled up, turning a graceful spiral into a wobbling mess. The Nazca, though, worked with nothing but wooden stakes and ropes, clearing the dark surface stones to reveal the lighter earth beneath. One theory suggests they might have used a grid system, mapping smaller sections onto the desert floor like a giant paint by numbers. But without written records, we're left guessing how they ensured consistency across hundreds of yards. The real puzzle lies in the purpose. Were these sacred pathways for rituals, astronomical calendars, or messages to gods in the sky? Some lines align with solstices, while others point to distant water sources, a lifeline in this parched landscape. Yet the most haunting possibility is that the Nazca never intended for their work to be seen as a whole. They might have created these designs for the joy of the making itself, trusting that the gods above would appreciate their devotion. Today, with satellite imaging and laser scanning, we can admire their precision in ways the Nazca never could. But in a quiet way, that's the point. These lines are a reminder that human ingenuity doesn't always need technology sometimes. It just needs vision, patience, and a willingness to create something larger than ourselves. The gleaming blade of a Damascus steel sword isn't just a weapon, it's a riddle wrapped in rippling waves of metal. For centuries, warriors from the Crusades to the Mughal Empire revered these blades for their impossible sharpness, capable of splitting a hair lengthwise or cleaving through armor without losing their edge. But by the 18th century, the secrets of their creation vanished, leaving behind only legends and frustrated scientists. Modern metallurgists can forge something that looks like Damascus steel, but the original process, our alchemy of rare ore, precise heat, and rhythmic folding remains just out of reach. What sets true Damascus steel apart isn't just its iconic watery pattern, but its molecular harmony. The steel's legendary toughness came from an intricate dance of carbon nanotubes and carbide bands, structures so advanced we only confirmed their existence with electron microscopes in the 21st century. Somehow, medieval blacksmiths in Syria and Persia achieved this nanostructure without thermometers or chemistry labs. They started with Wootz steel, a rare ingot imported from India, rich in trace elements like vanadium and tungsten. When heated and hammered in a specific sequence, these elements formed microscopic layers that interlocked like a natural chainmail, making the blades nearly unbreakable. Experiments to recreate the steel have stumbled over two major hurdles, the lost ore and the lost rhythm. The original Wootz mines in India were exhausted centuries ago, and modern substitutes lack the exact mineral cocktail. Even when researchers sourced similar ore, the forging technique proved maddeningly elusive. Too much heat and the carbon structures dissolved, too little and the layers wouldn't fuse. Some theories suggest the blades were quenched in exotic coolants like pomegranate juice or animal urine, while others point to cyclic heating, reheating the steel dozens of times at precise intervals to coax out its hidden strength. The closest modern equivalent, pattern-welded steel, mimics the look but not the magic. Today's blades are layered and folded to create visual waves, but they lack the self-sharpening carbide edges of true Damascus. In a twist of irony, nanotechnology labs now study these ancient swords for clues to developing stronger materials, from spacecraft alloys to unbreakable medical tools. Standing in a museum before a 900-year-old Damascus blade, you're left with a humbling thought. Its makers didn't just craft a weapon, they encoded a secret into the steel, one we're still trying to decode. And somewhere in the echoes of their hammers, there's a lesson that the past's greatest innovations weren't just about skill, but about listening to the hidden language of materials themselves. At the bottom of the Aegean Sea, encrusted in centuries of marine growth, lay a lump of corroded bronze that would rewrite history. When divers recovered the Antikythera Mechanism in 1901, they initially mistook it for a piece of shipwreck debris. But beneath the grime hid an artifact so advanced, so bewilderingly precise, that it took over 100 years of X-rays and CT scans to reveal its true nature, a celestial calculator capable of predicting eclipses, tracking Olympic cycles, and mapping the erratic dance of planets across the sky. What stuns researchers isn't just its complexity. It's the fact that this intricate clockwork of interlocking gears was crafted in the 1st century BCE, over 1,000 years before similar devices appeared in medieval Europe. The mechanism's inner workings resemble a miniature universe, with 37 precisely cut bronze gears simulating the motions of the sun, moon, and 5 known planets. One dial even accounted for the elliptical orbit of the moon, a subtlety ancient Greeks shouldn't have understood without Kepler's laws of planetary motion. Modern engineers attempting reconstructions face a paradox. The device's precision rivals that of 18th century Swiss watches, yet it was made with tools we'd consider primitive. The gears were hand-cut with files, their teeth spaced within fractions of a millimeter to ensure smooth meshing. Some researchers speculate the Greeks used a primitive lathe or template system, but no evidence of such technology has ever been found. Perhaps the most baffling aspect is the knowledge encoded in its design. The mechanism's eclipse predictions relied on the Saros cycle, a complex 18-year pattern of lunar and solar alignments. While Babylonian astronomers documented this cycle, applying it to a mechanical model required an unprecedented fusion of mathematics and craftsmanship. Even more startling, the device accounted for the 4-year cycle of the ancient Olympics, proving it wasn't just a scientific instrument but a cultural calendar, blending celestial mechanics with human tradition. Today, cutting-edge labs have produced working replicas using 3D printing and computer modeling, but these modern versions rely on materials and tolerances the Greeks couldn't access. The original builders worked without micrometers, without precision casting, even without the concept of zero in their number system. Their achievement stands as a haunting reminder that ancient brilliance often outpaced the tools available, and that some innovations vanish not because they were surpassed, but because the minds that conceived them took their secrets to the grave. Holding a fragment of the Antikythera Mechanism, you're left with a humbling thought. 2,000 years ago, someone held this same bronze gear, turning it gently as they charted the heavens. Their names are lost, their workshops dust, but in these delicate teeth and axles, we catch a fleeting glimpse of genius, one that still whispers across the centuries, challenging us to decode its mysteries. The Leaning Tower of Pisa defies gravity with a kind of stubborn elegance, its tilt so iconic that it's become a global symbol of imperfection. But here's the irony, that very flaw is the reason it's still standing. While modern skyscrapers rely on computer models and soil samples to stay upright, medieval builders crafted Pisa's tower with nothing but intuition and a willingness to adapt, and in doing so, they accidentally created one of history's most resilient structures. The tower's secret lies beneath the surface. Its foundation, just 10 feet deep, rests on unstable clay and sandy soil, a recipe for disaster by modern standards. Within 5 years of construction, the tower began tilting, and by the time builders reached the 3rd level, the lean was undeniable. Instead of abandoning the project, they adjusted. Each subsequent floor was built slightly taller on the sinking side, a subtle counterbalance that redistributed weight. Later, when the tower threatened to topple entirely, engineers added the iconic bell chamber at an angle opposite the lean, acting like a keystone to lock the structure in place. What's baffling is that these medieval fixes worked better than centuries of modern interventions. In the 1990s, a team of engineers spent 11 years and over $30 million trying to stabilize the tower with soil extraction and anchored cables. Their high-tech solution succeeded, but only after studying the tower's original foundation for clues. The builders' makeshift adjustments had created a dynamic equilibrium, allowing the tower to settle into the soft earth without collapsing. Modern soil analysis shows the ground beneath Pisa behaves almost like a fluid, shifting with moisture and pressure. Yet the tower moves with it, swaying imperceptibly like a tree rooted in wind. The real mystery isn't just how it stands, it's why similar modern structures fail. Contemporary buildings on unstable ground often require deep pilings or reinforced concrete rafts, solutions that fight the earth rather than work with it. Pisa's builders, lacking geotechnical surveys, embraced the imperfection. Their tower isn't just leaning, it's in conversation with the ground beneath it, a dance of give and take that's lasted 800 years. Standing in its shadow today, you're left with a humbling thought. Sometimes the greatest engineering isn't about forcing stability, but mastering balance. And in that, the tower's medieval creators might have been centuries ahead of their time. Stand in the center of Epidorus' ancient theater in Greece, drop a coin on the stone stage, and the sound will carry with crystalline clarity to the very last row 60 rows up nearly 200 feet away. No microphones, no speakers, just flawless geometry carved into a hillside over 2,000 years ago. This isn't an isolated marvel. From the grand theaters of Rome to the Odeons of Ephesus, ancient architects mastered acoustics so precise that modern engineers still can't replicate them without digital assistance. The secret lies in a symphony of design choices, each one a stroke of genius that modern science is only beginning to decode. First, consider the shape. Unlike modern concert halls with flat ceilings and right angles, ancient theaters were semicircular, with steeply tiered seating that acted like a natural sound funnel. Every surface from the stage floor to the limestone seats was carefully calculated to reflect and amplify sound waves. Researchers using laser scans discovered that the rows of seats function like acoustic filters, dampening low-frequency background noise like the murmur of a crowd, while enhancing higher frequencies like an actor's voice. Even the spacing between seats plays a role. The precise intervals create a phenomenon called acoustic diffraction, bending sound waves upward instead of letting them dissipate into the open air. But the real magic might lie in the materials. The Greeks and Romans didn't just carve their theaters from any stone. They selected varieties with specific resonant properties. Epidorus limestone, for example, has a porous texture that absorbs just enough sound to prevent echoes while still projecting clarity. Modern attempts to copy this effect often fail because contemporary concrete lacks the same microscopic cavities and mineral composition. In one experiment, a team built a replica using modern materials. Despite matching the dimensions exactly, the sound quality was noticeably inferior, proof that ancient builders understood their stone in ways we've forgotten. The most baffling part, there's no evidence the Greeks or Romans understood the physics of sound as we do today. They had no concept of wavelengths or frequency modulation, yet they achieved near-perfect acoustics through observation and iteration. Some scholars believe they used water-filled bowls as primitive sound mirrors, testing reflections during construction. Others suggest actors themselves guided the design, noting how their voices carried in different spaces. Whatever their methods, the results speak for themselves literally. Today, architects designing concert halls spend millions on computer simulations and adjustable panels to chase the same effect. Yet, even with these tools, they often rely on hidden speakers to compensate for dead zones. Standing in an ancient theater, you realize something profound. These structures weren't just built for art. They were instruments themselves, crafted to harmonize with the human voice in a way that still feels almost supernatural. And perhaps that's the greatest lesson, that perfection isn't always about advancing technology, but about deepening our connection to the world's natural rhythms. High in the mountains of Shaanxi Province, China, stands the Yinxian wooden pagoda, a 67-meter-tall tower that has weathered over 1,000 years of earthquakes, storms, and wars without a single nail or drop of glue holding it together. Its secret, a labyrinth of interlocking wooden brackets known as dugong, an ancient engineering marvel that modern architects still struggle to fully replicate. Picture a three-dimensional puzzle where each piece flexes just enough to absorb shocks but never enough to collapse. A design so effective that during the Great Earthquake of 1303, records describe the pagoda swaying like a reed in the wind while stone buildings crumbled around it. The genius of dugong lies in its paradox. It's both rigid and fluid. Each bracket is carved to fit snugly into its neighbor, transferring weight downward through a network of joints that tighten under pressure. When seismic waves hit, the structure shifts slightly, dissipating energy through friction between the wooden layers. Modern engineers call this passive damping, a principle used in today's skyscrapers with steel shock absorbers. But here's the catch: while our solutions rely on synthetic materials and precise calculations, the Chinese system used nothing but hand-carved wood and an intuitive grasp of balance. Attempts to recreate dugong with computer modeling often fall short. In 2016, a team at Kyoto University built a scaled-down pagoda using traditional methods and subjected it to simulated quakes. The model survived shakes equivalent to a magnitude 7.5, but researchers noted a critical difference. Historical dugong structures had subtle imperfections, tiny gaps, and uneven surfaces that actually improved flexibility. Modern CNC-cut replicas, with their machine precision, lacked this organic adaptability. It's as if the original builders understood something we've forgotten: perfection in stiffness can be a weakness. Perhaps the most humbling detail comes from the pagoda's maintenance records. Over centuries, caretakers replaced individual brackets as they wore out, always copying the original designs but never rigidly enforcing uniformity. The result, a living structure that evolved slightly with each repair, its resilience rooted in variation rather than standardization. Today, as engineers grapple with the limitations of brittle modern materials, the dugong whispers a lesson from the past. Sometimes the strongest things are those that know how to bend. Rising from the jungles of Java like a stone mandala frozen in time, Borobudur is a mountain-turned monument, a pyramid of wisdom built from 2 million volcanic stones, each carefully placed without mortar, without adhesive, without any of the modern tricks we rely on to keep structures standing. What's astonishing isn't just its scale, it's the way this 9th-century masterpiece defies the very ground it's built on. The temple sits atop a natural hill, yet its base doesn't crack or settle, even as the earth shifts beneath it. Modern engineers have run simulations calculating the weight distribution of its 10 terraces, and the results are baffling. Borobudur's builders achieved a near-perfect balance, compensating for uneven terrain with a precision that would require computer modeling today. The secret lies in the stones themselves. Unlike modern construction, where uniform blocks are stacked like Lego bricks, Borobudur stones are subtly irregular. Each one was hand-carved to fit its neighbor, creating a jigsaw puzzle where the gaps aren't flaws, they're features. When pressure shifts, the stones redistribute the load through friction and interlocking grooves, a principle similar to the Inca's earthquake-resistant walls but on a colossal scale. During the 2006 Yogyakarta earthquake, which destroyed thousands of modern buildings nearby, Borobudur didn't just survive, it barely trembled. Attempts to replicate this stability have stumbled over a paradox. The temple's strength comes from its imperfections. In a test project, engineers tried rebuilding a section using laser-cut stones for perfect alignment. The result, a rigid structure that cracked under stress. Borobudur's original builders understood something we often overlook. Nature isn't uniform, and neither should be the structures that rise from it. Their stones breathe with the land, shifting microscopically to absorb shocks without breaking. even more remarkable is how they managed this without blueprints or written records. The entire design encodes Buddhist cosmology, with each terrace representing a stage of enlightenment. The builders didn't just calculate weight, they harmonized physics and philosophy, crafting a monument where spiritual ascent and structural integrity are one and the same. Today, as we reinforce concrete with steel rebar and synthetic adhesives, Borobudur stands as a silent challenge. True resilience might not come from fighting nature's chaos, but from dancing with it. In the scorching deserts of ancient Persia, where summer temperatures could melt stone, architects devised a masterpiece of passive cooling windcatchers. These towering structures, some rising over 100 feet, turned blistering winds into refreshing breezes without a single watt of electricity. Picture a slender chimney crowned with vertical slots, strategically angled to capture even the faintest wind. As air rushed down the central shaft, it passed over water channels or cool subterranean spaces, dropping in temperature before spilling into homes below. The result, a natural air conditioning system so effective that indoor spaces could be 20 to 30 degrees cooler than the outside centuries before refrigerants or compressors existed. What stuns modern engineers isn't just the concept, but the precision. Windcatchers weren't generic towers, their designs were hyper-localized. In Yazd, Iran, they face northwest to catch prevailing winds, while in coastal regions, they're shorter and broader to harness sea breezes. Some even had adjustable vents to control airflow, a feature modern passive cooling systems struggle to replicate without mechanical parts. In 2019, a team from the University of Cambridge attempted to model these structures using computational fluid dynamics. They found something astonishing. The ancient builders had intuitively optimized airflow patterns that scientists now confirm reduce turbulence and maximize cooling. The real magic lies in the multi-purpose genius of these structures. Windcatchers didn't just cool air, they purified it. As wind descended, dust particles settled in specially designed chambers, while the evaporative effect from water basins added humidity to the dry desert air. Compare this to today's energy-guzzling AC units, which often leave air sterile and brittle. Even more impressive, some windcatchers doubled as ventilation systems, using temperature differences between day and night to create a natural convection cycle, flushing stale air out and pulling fresh air in. Modern architects trying to revive this technology face two hurdles: lost knowledge and misplaced priorities. Contemporary, green buildings often use solar panels to power fans mimicking windcatcher effects, a solution that feels almost ironic when the original required zero energy input. A 2022 project in Dubai attempted a hybrid approach, combining ancient windcatcher designs with photovoltaic panels. The result was efficient, but tellingly, it still couldn't match the cooling capacity of a purely passive 14th century tower in central Iran. Standing in the shadow of a 1,000-year-old windcatcher, you're struck by a quiet revelation. These weren't just clever buildings, they were dialogues with the environment, crafted by people who understood that true sustainability isn't about dominating nature, but collaborating with it. And in an age of climate crises and energy shortages, that lesson might be their most enduring gift. Snaking through the Andes at altitudes that would leave modern road crews gasping for air, the Inca highway system is a marvel of precision. A network of roads so straight, they seem to defy the very mountains they cross. Stretching over 24,000 miles, these pathways cut through some of the most brutal terrain on Earth: sheer cliffs, dense jungle, and jagged peaks. Yet despite the natural chaos, the roads rarely waver. Modern engineers using laser levels and GPS still struggle to maintain such unwavering straightness over even a fraction of the distance. How did the Inca, without theodolites or even the wheel, achieve this feat? The answer lies in a lost art of surveying, one that turned geography into geometry. The brilliance of these roads isn't just their straightness, it's their adaptability. Where the land rose too steeply, the Inca built staircases carved directly into bedrock, each step uniform in height to prevent fatigue. Where valleys dipped, they suspended fiber bridges strong enough to support armies yet flexible enough to sway with the wind. But the most baffling sections are the stretches where the road clings to cliff faces, its edges perfectly parallel despite the dizzying drop below. Researchers have found evidence of simple but effective tools, knotted ropes for measuring, wooden stakes for alignment, yet these alone don't explain the precision. Some theorize the Inca used reflected sunlight or water-filled trenches as natural levels, aligning roads with celestial markers for long-distance consistency. What's even more remarkable is the efficiency. Unlike modern highways that bulldoze through obstacles, Inca roads worked with the land. Curves were minimized not for convenience, but for speed. Messengers running the network could relay information from Quito to Cusco, a distance of 1,200 miles, in under a week. The secret, a design philosophy that prioritized directness over ease. Where a modern road might zigzag up a slope to reduce incline, Inca engineers often opted for punishingly straight ascents, knowing their relay runners, trained since childhood, could handle the vertical challenge. Today, satellite imagery reveals something startling. Many of these roads deviate less than a meter over kilometers, a tolerance rivaling modern freeways. But here's the twist. They achieved this without written plans or standardized units of measurement. Instead, local teams built segments using their own body parts for reference, a forearm's length, a stride, yet somehow ensured seamless connections at meeting points. It's as if the entire empire shared an unspoken understanding of space and distance, a collective intuition modern technology can't replicate. Walking these ancient paths, you're left with a humbling realization. Straight lines aren't just about tools. They're about vision, and the Inca saw the world with a clarity we're still straining to match. Beneath the turquoise waves off Japan's Yonaguni Island lies a puzzle carved in stone, massive terraces, staircases, and what appear to be perfectly angled platforms, all submerged under 60 feet of ocean. Discovered in 1986 by a diver searching for hammerhead sharks, these structures ignite a debate that still rages today. Are we staring at the handiwork of an ancient civilization, or merely the whims of geological chance? The answer, it seems, is as elusive as the ruins themselves. What makes Yonaguni so controversial are its uncanny features. The main monument, dubbed the Turtle, resembles a stepped pyramid with razor-straight edges and near-perfect 90-degree corners. Nearby, a pair of towering pillars stand like gatekeepers, their surfaces smoothed in ways that defy typical erosion patterns. Marine geologists point to the region's active tectonic activity, suggesting these formations could be sandstone naturally fractured into geometric shapes. But then there's the road, a long, flat pathway connecting structures with an alignment so precise, it mirrors ceremonial causeways found in terrestrial ancient sites. Diving deeper into the mystery, researchers have uncovered even stranger details. Carved channels run along certain walls, resembling drainage systems or ritual waterways. Circular depressions, too uniform to be random pockmarks, dot the surfaces like ancient mooring points. Most compelling, a humanoid face etched into one rock, its features weathered but unmistakably deliberate. Skeptics argue currents and marine life could create such illusions, but when scientists compared Yonaguni's angles to known natural formations, the math didn't add up. The probability of so many perfect geometries occurring together by chance, statistically negligible. Modern attempts to simulate Yonaguni's formation have only deepened the intrigue. In a 2012 experiment, geologists tried replicating the structures using sandstone blocks subjected to underwater erosion. After years of observation, the results were telling. While nature could produce some stepped shapes, the sheer complexity and repetition at Yonaguni remained unmatched. Even more puzzling is the site's age. If human-made, it would date back at least 10,000 years, predating any known civilization capable of such large-scale stonework. This timeline aligns with legends of a lost Pacific culture, but without definitive tools or artifacts, the theory lingers in the realm of speculation. Perhaps the most haunting clue lies in the ruins' orientation. Key features align with solstice sunrises, a trait shared by sacred sites worldwide. For now, Yonaguni remains a riddle wrapped in coral and currents. Whether it's nature's artistry or humanity's forgotten handiwork, one thing is certain: the ocean guards its secrets well, and some mysteries refuse to surface. Rising from the island of Pharos like a defiant challenge to the Mediterranean winds, the Lighthouse of Alexandria wasn't just a beacon, it was a skyscraper centuries before the word existed. At over 100 meters tall, it dwarfed every structure of its time, its polished limestone facade reflecting sunlight by day, and its massive flame visible from 35 miles out to sea by night. But what truly staggers modern engineers isn't its height, it's how this slender giant stood unshaken for over 1,600 years in one of the most tempestuous coastlines on Earth. Today, even with reinforced concrete and steel frames, constructing something so slender yet stable in hurricane-prone waters would be a gamble. The lighthouse's secret lay in its ingenious foundation, a fortress of submerged stone blocks shaped to break waves before they could erode the base. Ancient accounts describe a honeycomb-like matrix of chambers filled with molten lead to weight the structure, acting as a counterbalance against the wind's torque. Modern simulations show this design created a pendulum effect. When gusts hit, the upper sections swayed slightly while the weighted base absorbed the movement. But here's the catch: contemporary attempts to recreate this system fail because we lack the original builder's intimate knowledge of local geology. The lighthouse didn't just sit on the seafloor, it was anchored to a natural limestone outcrop that acted like a living extension of its foundation, something modern sonar mapping only recently revealed. Then there's the mirror, or was it a flame? Classical texts contradict each other, with some describing a colossal polished bronze reflector that could focus sunlight into a deadly beam. Legend claims it burned enemy ships, while others insist on an eternal fire fed by resinous wood. The truth might be both. A 2018 study proposed a hybrid system. During the day, curved mirrors, possibly made of parabolic copper sheets, would harness sunlight, while at night, fires amplified by the same reflectors pierced the darkness. Experimental reconstructions using period-accurate materials achieved startling results, projecting light over 20 miles. Yet without the lighthouse's exact elevation and mirror curvature, we'll never know its full potential. The most humbling realization: the lighthouse's architects worked without photometric calculations or wind tunnel testing. They understood aerodynamics through observation: how seabirds' wings cupped the wind, how reeds bent but didn't break. Their tower tapered at just the right angle to slice through gusts, its exterior staircase spiraling counter-clockwise to counteract prevailing winds. Modern coastal towers, rigid and straight, often require dampers and guy wires to survive storms, but the lighthouse danced with the wind, its very flexibility its strength. When it finally fell in the 14th century, it wasn't the sea or storms that toppled it, it was an earthquake so massive, it would devastate even today's sturdiest structures. Standing on Alexandria's shores today, staring at the fort built from the lighthouse's ruins, you're left with a haunting thought. We've conquered height with steel and glass, but we've yet to match the elegance of stone that touched the clouds and laughed at the wind. Imagine sailing across the North Atlantic under thick, overcast skies, no stars, no sun, just a featureless gray void stretching to the horizon. For most sailors, this would spell disaster, drifting blindly until land or luck intervened. But Viking navigators faced these conditions routinely, crossing thousands of miles of open ocean with nothing more than a sliver of crystal to guide them. These so-called sunstones, mentioned in medieval sagas and later dismissed as legend, turned out to be one of history's most ingenious navigation tools. Modern experiments reveal they could locate the sun's position with eerie accuracy, even when hidden behind clouds or just below the horizon. Yet despite decades of study, scientists still can't fully replicate their precision without resorting to modern technology. The magic lies in a property called polarization. Certain crystals like Iceland spar, a transparent form of calcite found in Viking graves, filter sunlight in unique ways. When held toward the sky, the stone splits light into two beams, creating overlapping images. By rotating the crystal until these images match in brightness, a navigator could pinpoint the sun's location to within a few degrees, day or night. In 2011, a team from Hungary's Eötvös University tested this method aboard a replica Viking ship. Under heavily overcast conditions, their sunstone readings were accurate enough to maintain a course within 40 miles after 4 days at sea, a margin of error that could mean the difference between reaching Greenland or vanishing into the ice. But here's the catch: modern attempts to use sunstones hit a snag. Without the Vikings' intimate knowledge of their local crystals, the technique falters. Not all calcite works equally well. Subtle variations in clarity and structure affect accuracy. Researchers speculate that Viking navigators curated their stones carefully, selecting only those with optimal optical properties through generations of trial and error. Even more baffling, the sagas mention sunstones being used at twilight or during the polar winter's perpetual gloom conditions where modern instruments struggle to detect polarization at all. Some theories suggest Vikings combined the crystals with other cues, like wave patterns or bird behavior, creating a holistic navigation system we're only beginning to understand. What makes this discovery humbling is the contrast with today's reliance on satellites and gyroscopes. Our systems are precise but fragile, vulnerable to solar flares, jamming, or simple battery failure. The Viking solution required no power, no maintenance, just a keen eye and a piece of the Earth itself. In an age where we've mapped every inch of the planet, their sunstones whisper a reminder: sometimes the most advanced technology isn't the one with the most circuits, but the one that listens closest to the natural world. Standing in the shadow of an Egyptian obelisk, it's hard not to feel dwarfed, not just by its height, but by the sheer audacity of its creation. These monolithic spikes of granite, some weighing over 400 tons, weren't pieced together like modern skyscrapers. They were carved, wrestled from the earth in one flawless piece, then transported hundreds of miles across deserts and rivers to stand upright in city squares and temple complexes. The logistics alone boggle the mind. Picture a stone column as tall as a 10-story building, as heavy as 200 cars, and as precise as a Swiss watch. Now imagine moving it without trucks, without cranes, without even the wheel. This wasn't just construction. It was a high-stakes ballet of physics and brute force, and modern engineers still can't quite figure out how they pulled it off. Take the unfinished obelisk of Aswan, still lying in its quarry like a sleeping giant. Had it been completed, it would have been the largest ever attempted, 42 meters long and weighing nearly 1,200 tons. The cracks that doomed it reveal something extraordinary. workers carved it from the bedrock in situ, chiseling downward along its entire length to free it from the earth. This wasn't haphazard chipping. The sides are smooth to within a millimeter over their entire surface. Modern diamond-tipped saws struggle to achieve such precision, yet the Egyptians did it with nothing but dolerite hammers and copper chisels. The real puzzle, how they planned to lift it. The quarry floor slopes slightly, meaning the obelisk would have had to be rotated 90 degrees and raised upright, a maneuver that would challenge today's heaviest cranes. Then there's the transport mystery. How do you move a 400-ton needle of stone 600 kilometers down the Nile without it sinking your barges? Wall paintings in Hatshepsut's temple show obelisks lashed to giant sledges dragged by hundreds of workers, but the math doesn't add up. Granite's friction against sand would require implausible manpower unless the Egyptians knew tricks we've forgotten. In 2019, a team tested a theory. Wetting the sand ahead of the sledge reduces friction by half, creating a slick path. It works for small loads. Scaling up to obelisk weight introduces terrifying variables. One misstep and the stone crushes its handlers. Yet somehow, the Egyptians moved dozens of these monoliths without a single recorded disaster. The grand finale, raising the obelisk, defies logic even more. Modern attempts using replica sledges and earthen ramps have ended in near catastrophes. In 2001, an experimental archaeology team tried to erect a 25-ton replica. Despite steel cables and safety gear, the obelisk nearly toppled, saved only by emergency supports. The Egyptians, though, left no evidence of ramps or scaffolding at erection sites. One radical theory suggests they might have used counterweighted pivots, rocking the obelisk upright like a seesaw, a technique requiring split-second coordination. But with stakes this high, there's no room for error. A single slipped rope would send hundreds of tons crashing down. What's humbling isn't just their success, it's their consistency. The Luxor obelisk, now in Paris, and its twin in Rome share identical proportions despite being carved centuries apart. This wasn't luck, it was institutionalized mastery, a craft refined through generations. Today, we've mastered steel and concrete, but the obelisks whisper a taunt. True genius isn't just about force, but finesse. And in their shadow, we're left wondering, did they possess secrets lost to time, or simply a patience we've outgrown? Descending into the Stepwells of Gujarat feels like stepping into an inverted cathedral, a sacred space carved not toward the heavens, but into the very earth itself. These aren't just reservoirs, they're feats of hydroengineering so precise, they put modern water management systems to shame. Take Chand Bayori, one of the deepest stepwells in India. 13 stories of symmetrical staircases cascading down to a shimmering pool, with every step, every corridor, designed to harness and conserve every precious drop of monsoon rain. What's baffling isn't just the scale, it's the science. Without hydrology textbooks or computer models, ancient builders crafted structures that naturally cooled water, minimized evaporation, and even purified it through layers of sand and charcoal. Today, engineers studying these wells are uncovering principles we've only recently discovered in sustainable design. The real mystery lies in the stepwells' dual purpose. By day, they functioned as communal gathering spots, their shaded lower levels offering respite from blistering heat. By night, they transformed into ritual spaces, their steps illuminated by oil lamps reflecting off the water, an early form of liquid-cooled architecture. Modern attempts to replicate this passive cooling effect often fail because we overlook the subtle genius of their construction. The steps aren't just functional, they're carefully staggered to create microclimates. As air descends, it's cooled by the water's surface, then circulates back up through ventilation shafts hidden in the walls. Contemporary architects in arid regions have tried mimicking this with solar-powered fans, but the originals achieved it with nothing but stone and airflow. Then there's the water management. Stepwells like Ronnie Kai Vav feature intricate channels that funnel rainwater through a series of filters, removing sediment before it reaches the main reservoir. Some even include water gates, sluices that could be adjusted to control flow during droughts or floods. In a 2018 study, hydrologists mapped these channels and found something astonishing. The gradient of each slope was calibrated to slow water just enough to let impurities settle, a technique modern treatment plants replicate with chemical flocculants. The builders' understanding of fluid dynamics was so advanced, their designs could handle seasonal deluges without erosion, something today's concrete storm drains struggle with. Perhaps the most humbling detail is the stepwell's resilience. While modern dams silt up and reservoirs crack, these ancient structures have functioned for over a millennium with minimal maintenance. Their secret, adaptive design. Unlike rigid contemporary systems, stepwells flex with the environment. During dry seasons, the exposed steps absorb heat, creating convection currents that draw moisture from the soil. When rains return, the same steps become spillways, dispersing energy to prevent erosion. It's a dialogue with nature, not a conquest. Standing at the base of a Dalaj stepwell, watching sunlight dance across its carved deities and geometric patterns, you're struck by a realization. These weren't just feats of engineering. They were acts of reverence, a reminder that the most advanced technology isn't always the loudest, but the one that listens to the whispers of the earth. And in their silent depths, they hold answers we're only beginning to thirst for. High above the jungles of Central America, the ruins of Mayan observatories stand as silent witnesses to a celestial understanding that defies time. At sites like El Caracol in Chichen Itza, narrow slit windows and precisely aligned staircases frame the movements of Venus, the Sun, and the Moon with eerie accuracy. What stuns modern astronomers isn't just their ability to track these cycles, it's their precision. The Mayan long count calendar calculated a solar year at 365.242 days, just 17 seconds shorter than our modern measurement. For perspective, that's like using stone tools to measure a heartbeat from a mile away. The real mystery lies in how they achieved this without telescopes or written numerals. Mayan astronomers worked with a base 20 numbering system and a concept of zero so advanced, Europe wouldn't adopt it for another 1,000 years. Their Dresden Codex, a bark paper book surviving centuries of humidity, contains Venus tables accurate to 2 hours over 500 years. Modern software can replicate these calculations, but the Mayans did it with knotted strings and shell counters, their observatories functioning like analog computers. At Capon, staircases double as timelines, each step marking a cycle of eclipses, with notches correcting for lunar wobbles that even Newton's physics couldn't explain. Perhaps most haunting is their prediction of cosmic events we've only recently verified. The Temple of the Inscriptions at Palenque encodes a date in 2012 that once sparked apocalyptic fears, but Mayan scholars now recognize it as a reset point in their cyclical timekeeping, aligning with a rare galactic conjunction NASA confirmed occurs every 26,000 years. How did a civilization without optics pinpoint celestial events on scales we measure with radio telescopes? The answer might lie in their obsession with patterns. By tracking generations of scribes recording the same celestial events, they compiled datasets rivaling modern observatories. Today, archaeologists using LiDAR scans have uncovered hidden observatories where entire buildings align with solstice sunrises or Venus's extremes. Yet for all our technology, we've found no instruction manual, just stones whispering a truth we're still decoding. In their shadows, you realize the Mayans didn't just watch the stars. They listened, and somewhere in that silence, they heard the universe's rhythm with a clarity we've yet to match. Hidden deep in the Cambodian jungle, Angkor Wat doesn't just dominate the landscape, it defies it. This sprawling temple complex, larger than modern Paris, was built without bulldozers, without steel, and without the mathematical notation we rely on for precision. Yet every courtyard, every tower, and every inch of its 5 million-ton sandstone structure aligns with celestial events and earthly symmetries so precise, modern engineers still can't fully explain how the Khmer Empire pulled it off. Start with the basics, moving those stones. The temple's sandstone blocks, each weighing up to 2 tons, were quarried from Mount Kulin over 50 kilometers away. Historians long assumed they floated down the Siem Reap River on rafts, but recent sediment studies reveal a problem. The river didn't exist when Angkor Wat was built in the 12th century. Alternative theories suggest an intricate network of canals, but no trace of such waterways has been found. Even more perplexing, the stones fit together so tightly that many joints don't even need mortar. Laser scans show gaps of less than half a millimeter between blocks, a tolerance rivaling modern machine-cut masonry. Then there's the cosmic choreography. During the spring and autumn equinoxes, the sun rises directly over Angkor Wat's central tower, a phenomenon requiring alignment accurate to a fraction of a degree. The temple's outer moat, stretching over 5 kilometers, mirrors the Milky Way's path as seen from Earth, an astronomical map carved into the landscape. Modern attempts to replicate this celestial mirroring using satellite surveys and 3D modeling still result in slight deviations. The Khmer builders achieved this without telescopes, without written star charts, likely using nothing but shadow poles and generations of observational records passed down orally. But the real enigma lies beneath the surface. Ground-penetrating radar has revealed an underground grid of channels and chambers, some filled with tightly packed sand. Engineers speculate this acted as a dynamic foundation, absorbing seasonal floods that would have destabilized rigid structures. When monsoon rains swelled the moats, the water pressure compressed these sand layers, creating a self-adjusting buffer against erosion. Contemporary architects testing this theory found it reduced structural stress by nearly 40% compared to conventional foundations. Yet no other civilization is known to have used this technique, leaving us to wonder, did the Khmer discover it by accident, or was it the product of a lost school of engineering? Perhaps the most humbling detail is Angkor Wat's resilience. While modern concrete jungles crack and warp within decades, these sandstone towers have weathered 800 years of monsoons, earthquakes, and jungle encroachment. Their secret might lie in the stones themselves. Microscopic analysis shows the Khmer selectively used sandstone rich in quartz for load-bearing sections, a mineral that hardens under pressure. Non-critical areas used softer stone, allowing subtle flex during tremors. This gradient of materials creates a structure that's both rigid and forgiving, a balance modern seismic engineering strives to achieve with synthetic composites. Standing on Angkor Wat's upper terrace at dawn, watching sunlight glide across its carved celestial nymphs and warrior kings, you're struck by a realization: this wasn't just a temple. It was a dialogue between earth and sky, a testament to what happens when human ambition harmonizes with nature's rhythms. And in its shadow, our brightest minds are left with a silent challenge to build not just for the present, but for the millennia. Even with robotic arms, computer simulations, and space-age materials, modern engineers often hit a wall when trying to recreate ancient construction marvels. It's not just about lacking the right tools, it's about missing the living knowledge that turned raw stone and sweat into timeless monuments. Consider the Roman concrete we discussed earlier. Labs can analyze its composition down to the atomic level, but without the exact volcanic ash from Pozzuoli or the centuries-long curing process, modern versions still crumble faster. This isn't a failure of technology, it's a gap in understanding how materials and time interact in ways no spreadsheet can predict. Take the manual skill of ancient artisans. The precision of Borobudur's interlocking stones or the Inca's mortarless walls wasn't just about careful measurement, it was about tactile intuition. Builders spent lifetimes apprenticing, their hands learning the language of stone in a way that machines can't replicate. A CNC router might carve a perfect block, but it can't feel when a stone's natural grain requires a slight adjustment, like the Inca's intentional imperfections that made their walls earthquake-proof. Modern attempts often fail because we prioritize uniformity over adaptability, forgetting that ancient builders worked with nature's irregularities, not against them. Then there's the mystery of lost materials. The Damascus steel swords we marvel at today depended on Wootz ingots from long-exhausted Indian mines, their unique mix of trace elements irreplaceable. Even if we could source identical ore, the rhythmic hammering and heating techniques passed down through generations of blacksmiths left no instruction manual. It's like trying to bake a legendary chef's bread using only a list of ingredients. Without their instincts for timing and texture, the result falls flat. But perhaps the most humbling challenge is scale. Modern construction thrives on speed and efficiency, yet ancient projects embraced timelines we'd consider unthinkable. The Great Pyramid took roughly 20 years, a blink in the lifespan of a civilization. Workers weren't racing against budgets, they were perfecting a craft meant to outlast eternity. Today's engineers, pressured by deadlines and cost margins, often lack the luxury of such patience. When a team tried carving a miniature Kailasa temple replica using traditional methods, they realized something profound. Rushing the process risked cracks, while the original builder's slow, deliberate strikes allowed the stone to speak its weaknesses. This gap between past and present isn't just about forgotten techniques, it's about differing philosophies. Ancient builders saw their work as a collaboration with the natural world, whether it was Mayan astronomers aligning temples with Venus or Persian architects harnessing desert winds for cooling. Modern engineering, for all its brilliance, often treats nature as an obstacle to overcome. The result, we might construct taller towers or dig deeper tunnels, but we're still playing catch-up when it comes to longevity and harmony. Standing in the shadow of these ancient wonders, we're left with a provocative thought. Maybe our greatest technological advancement would be to rediscover the patience, intuition, and reverence that turned ordinary materials into the extraordinary. After all, the true test of engineering isn't just what we can build, it's how long it endures. From pyramids to pagodas, these 24 ancient techniques stand as silent testimonials to human brilliance, proof that raw ingenuity often outpaces raw power. Today's cranes and bulldozers can erect skyscrapers in months, yet they still falter when asked to replicate the self-healing concrete of Rome or the earthquake-defying walls of Machu Picchu. It's not just about the tools, it's about the minds that wielded them. The builders of antiquity didn't just construct, they conversed with their materials, understanding stone, wind, and water as collaborators rather than obstacles. Consider the irony. We've landed rovers on Mars, yet we can't perfectly align a monument to true north without satellites, as the Egyptians did with nothing but shadows and stars. We've invented alloys stronger than steel, yet we've failed to recreate the nanostructured magic of Damascus blades. Our drills pierce miles into the earth, but we've lost the art of carving a temple from a single cliff face, as they did at Kailasa. This isn't a contest between past and present, it's a wake-up call. The real lesson of these ancient marvels isn't that they were better, but that they were different, born from a world view where time, patience, and harmony with nature weren't luxuries but necessities. What's haunting is how much knowledge has simply evaporated. The Incas left no blueprints, yet their mortarless masonry outlasts our steel-reinforced cities. The Roman concrete recipe vanished for millennia, only to be partially decoded by accident. How many other techniques disappeared into the shadows of history? The Viking sunstones, the Persian windcatchers, the Mayan celestial calendars, each represents a branch of human ingenuity that flourished, then faded, leaving behind whispers in stone and legend. But here's the hopeful part. These mysteries aren't dead ends. They're invitations. Modern scientists now study Damascus steel for next-gen nanomaterials, while Roman concrete inspires eco-friendly alternatives. Engineers probe Inca walls for seismic resilience clues, and passive cooling systems revive ancient windcatcher designs. The past isn't just a museum, it's a mentor, offering solutions to problems we're only beginning to face. So the next time you walk past a construction site or gaze up at a glass skyscraper, take a moment to wonder, what will endure? In 1,000 years, will our steel towers still stand? Or will it be the humble stepwells of India, the dancing walls of Peru, the whispering theaters of Greece? The ancients built for eternity, and somehow, against all odds, they succeeded. Their greatest secret might be this: true progress isn't just about moving forward, it's about remembering. If these engineering enigmas have left you as awestruck as they've left us, don't keep it to yourself. Share this video with someone who loves a good mystery. Hit that like button and subscribe to join us as we keep unraveling history's greatest puzzles. Because somewhere between the stones and the stars, the past still has plenty to teach us, if we're willing to listen.